Hello, my name is Hossein Talevi, and today I'll be talking about our work on NIMA, Neural Image Assessment. This has been a collaborative work with Peyman Milanfar. Here is an outline of the talk. First, I'll talk a little bit about the broad research areas on image quality assessment, or IQA. Then I move on to describing our work NIMA, which focused on learning from human ratings. Namely, I'll focus on two areas, the single stimuli and the pairwise learning. So each category focuses on a specific type of human ratings for IQA tasks. And finally, I'll comment on how an IQA model like NIMA can be used to guide image enhancement and restoration models. So, a few key questions that we try to answer in this talk are as follows. The first is, what if there was a way to aesthetically rank uh, these photos of sunset near the beach? Um, And by aesthetically, we mean semantic appeal of a photo at a higher level than just the technical level. Here are some examples of scores that come out of NIMA model trained for aesthetic assessment. These images are ranked with the NIMA score. The score is from 1 to 10, 1 indicating low quality and 10 being the highest quality. As you can see from top left to bottom right, if you traverse this list, you'll see that you may agree that the overall trend is that the aesthetic quality of the image or beauty and appeal of these images starts to decay. Here are a few more examples from the Eiffel Tower. Um, when you start to look at these trends, um, you may conclude that, okay, images on the top of the list have better dynamic range, better light, they have better composition, whereas the images on the bottom, um, maybe low light, maybe not the best composition, maybe the object of interest is not visible, so on and so forth. So these are the type of aesthetic qualities that an IQA model like NIMA is able um, to capture. The object of interest could be a person or a someone's a personal album. These are pictures of my co-author Peyman. As you can see on the top left, again, going down the list, you may agree that the overall trend looks reasonable. However, you may disagree on a specific ordering of these images. And that goes to the subjective nature of image quality assessment in general. A second question we try to answer is whether we can rank photos based on their technical quality. And the focus, instead of being on a high level aesthetic quality, can we shift that towards low level pixel quality um, and capture axes like blur, like exposure, so on and so forth. So this is NEMA model being trained to capture technical quality um, of the same scene. These images were captured at the same time in a time frame of maybe 3 minutes, and each one of them are a few seconds apart. You can see that the bottom of the list, you'll see images that are blurry, maybe because of the camera motion or the object motion. There could be also bad exposure. This is perhaps because of the camera auto exposure not working as it's intended to. Whereas images on the top of the list more or less are sharp and uh, the exposure seem to be reasonable. So when we use the term technical quality, we refer to pixel level qualities in an IQML. Here are a few more examples for technical quality. The quality issues could be degradation such as image compression, could be noise, or a combination of um, noise, blur, compression, so on and so forth. Again, the ranking, the scores that are provided here just give you a sense of what NIMA provides and can capture in an image. Few more examples. Again, very similar scenario in which I just mentioned, which is blur, compression, noise, and a combination. And these are, it could be synthesized, the degradation could be synthesized, or it could be um, a real type of degradation, such as in previous examples. A third key question that we try to answer is, okay, let's assume we do have this IQML. Could I use it to actually guide enhancement models? And the answer to that question is actually yes. And I'll describe how we develop NIMA model, and we used it in a framework to train an enhancement model to produce higher quality results than just the baseline supervised training. I'm going to first talk a little bit about the broad IQA research areas. Research areas in image quality assessment can be divided to four overlapping areas. On one hand, we have the problem of studying technical quality assessment. By technical quality, I refer to pixel level qualities such as noisiness, sharpness, blur, compression artifact, tone, color, so on and so forth. Second area which overlaps with the technical quality assessment is the assessment of aesthetic qualities. By aesthetic, I mean semantic level attributes that deal with appeal, beauty, and emotions in photos. The third area is the presence or the absence of a reference photo at the inference time to compare the quality of a given image. There are very well-known full reference metrics that have been used for decades, such as PSNR and more recently SSIM in this category. And lastly, um, there is the no reference quality assessment area in which uh, it typically tries to model human perceptual preference through subjective studies. And label data sets are typically leveraged to develop models or solutions for no reference quality assessment. Scope of NIMA is no reference metrics, and it covers both the technical quality assessment and aesthetic quality assessment. More specifically, for no reference aesthetic quality assessment, we focus on the AVA dataset, which was established in 2012. The source images and the ratings came from data sets that were rated by amateur photographers in photography contests. Um, The nature of this problem is very subjective, um, and it mainly deals with high level photographic attributes such as point of view, composition, framing, focus, depth, and so on and so forth. For no reference technical quality assessment, there are many data sets in the literature. Just to name a few, there is a list of three of them: TID Live and Cohen IQ, which is more recent. But most of these data sets, basically, what they represent is a list of quality attributes and scores that describe and quantify a very specific aspect of technical quality, such as noisiness, sharpness, colorfulness, so on and so forth, or they have overall mean opinion score describing the overall quality, or they may actually present both the mean opinion score as well as attribute scores. I'll talk about how NIMA is developed on both technical quality data sets as well as static quality data sets. The last aspect of um, uh, image quality assessment, specifically no reference quality assessment, is the way um, the rated data is curated. Namely, there are two broad methods for collecting human visual preference. On one hand, um, there is a simple method of showing a single image to a rater. Um, in the case of the AVA data set, it was the amateur photographers, and asking them to give a score from a range, for example, 1 to 10. Um, And on the opposite side, there is a second method, which is pairwise, in which the raters are asked to compare two images, image A versus B, for a very specific quality attribute or the overall quality attribute. Both of these methods have been widely used in the literature. I'll cover both. We'll first cover the single stimuli and how the NIMA model was trained on this data, and then we move on to the pairwise method. I'll first cover learning from human ratings with single stimuli um, data. Specifically, I'll cover aesthetic quality assessment first, and then I'll go over technical quality assessment. Uh, Just a little bit of background on the AVA dataset. I did mention that the dataset is based on photography contests. So amateur photographers rate images based on a specific themes and contest rules. For example, these are some examples from one contest with the theme stirs, and the scores on each image is basically the the mean score that was assigned to each particular image from a couple of hundred of amateur photographers' ratings. As you see, the higher the mean, uh, the aesthetic quality is actually showing itself. Just a reminder, the score is from 1 to 10. Here are a list of uh, contests from the AVA dataset. As you can see, the the themes are very diverse. There are roughly 1,400 contests that um, AVA has contributes to, and there are roughly a quarter million photos rated by an average of 200 photographers. If we look at the distribution of the mean on the left side, you can see that the data, the scores are quite skewed towards the score 5, 5.5. Um, but this mean score doesn't tell the whole story. If you look at the distribution of the standard deviation of the scores, you can see that actually this is the standard deviation has a mean of roughly close to 1.2, 1.3, which is not small. This sort of indicates how subjective the aesthetic quality assessment problem can be. And here is a joint um, distribution of the standard deviation and the mean score. Um, so, for instance, if you look at the mean score around 5, you'll see that there is actually quite a lot of images with standard deviation of above 1.5, meaning that the histogram of scores associated with these images is rather flat instead of um, eh, being skewed and rather compact. So, how do we train the NIMA model? Um, this has been a very common practice in machine learning, uh, in which uh, people grab an already trained image classifier, typically trained on ImageNet, and warm start their model on from those weights, and then fine tune it on the downstream task. In this case, image static assessment with the AVA dataset. Um, this practice is, broadly speaking, labeled as transfer learning, transferring learning from that um, baseline image classifier into a new task. And that has shown to be effective, and leveraging existing image classification models for tasks such as image aesthetic assessment. That's how NIMA is trained. More specifically, the building blocks of the model are you have the backbone, CNN. Think about it as it can be an inception model, MobileNet model, ResNet model, or even more modern transformers. What was used in NIMA was we tried a few different backbones, and inception seemed to produce the best results. Then we do add a spatial pyramid pulling. What the pyramid pulling does is effectively, instead of just average pulling, you apply average pulling on a grid of local windows that allows the pulled features to represent not just the overall aesthetic and semantic, but also local variations in the activations are better presented this way. Then we add a fully connected layer and the softmax layer. So if you remember, we talked about how the labels for an image in AVA are basically a histogram of ratings. And that's why we do have a softmax here. So we have a histogram with 10 bins. There are scores from 1 to 10, and instead of predicting the mean, we predict the histogram of ratings, or the distribution of ratings that is normalized. Think about them those as the score probabilities or the empirical probabilities. The training loss that we use is the EMD, the Earth Movers Distance Loss, and this has to this has shown to be effective for learning the distribution of ratings. Here are some examples of ground truth distribution of the scores, as well as the predictions from NIMA. There are three images on the left. The image on the left has relatively high aesthetic quality, and the images on the right has relatively lower static quality. And as you can see, the predicted distribution follows the trend of the ground truth. Also note that um, at times the distribution could be wider, which means that the ratings, or rather the raters, may have not agreed on a score. So that makes the IQA task more challenging, obviously because of the subjectivity of the problem. But by predicting the distribution of score, we can predict this behavior, meaning that we can predict how the human subjects would have rated an image. Here are some comparisons on the accuracy as well as linear and rank correlation of the mean scores. With some of the existing methods. Note that NIMA doesn't need to use any scene categorization or multiple passes of the input image. It's just basically a one-shot approach. We tried three different backbones, and the most effective one shown to be the Inception V2 model. Um, we also tried different configurations of the baseline model. We saw that adding complexity doesn't necessarily lead to better performance. One of the issues is obviously overfitting. Um, but technically, at a range of 2 to 3 billion flops, the model produced the best results at this specific training resolution. Next, I'll talk about training NIMA for predicting technical quality. Namely, I focus on the TID 2013 dataset. This dataset has roughly a bit over 3,000 images. And what you're looking at is the distribution of mean score and standard deviation. As you see, the range of the standard deviation scores is a lot smaller than the previous dataset AVA on static assessment, hinting at technical quality assessment being a less subjective task overall. Similar to the way NIMA was trained for predicting aesthetic quality, we trained the model for predicting the distribution of scores. We estimate the distribution of scores from their mean and standard deviation, although in TID, there was no histogram of scores associated with it, with each image. Um, Interestingly, for TID, the backbone that worked best was VGG16. And here you're looking at um, the linear correlation coefficients and rank correlation coefficients. So moving from a single stimuli to pairwise, um, pairwise learning is tends to be a more challenging task for training the ML models, and perhaps easier for collecting data from raters. This approach has been widely adopted in um, many of the existing research folks as well as in the industry. Uh, Once the pairwise data is curated, an ML model can be trained through mini batch learning with a loss such as cross entropy, for example. However, the challenge with learning from pairwise comparisons is that at each training step, the model only sees the relative distance between sample A and sample B, and it does not have access to learn from information that is obtained globally and contains and represents the global ranking of the data. So the curation phase is asking a rater to select from image A and image B based on overall quality or a very specific quality attribute such as sharpness, exposure, compression, artifacts, so on and so forth. Um, Typically, these type of comparisons are made on a subset of all possible pairs. Um, we call these ratings local comparisons because they compare an item I, item J. The reason, and this cannot scale as well as the single stimuli, is that to gather and curate all the possible ratings, one would have to create O of n squared pairs and basically rate these images with multiple human subjects. The reason you need to have multiple um, human subjects is that you want to reduce the subjectivity and be able to have multiple ratings to average, for instance, to lower the possible noise in the labels. One can look at these sort of empirical preferences from the maximum likelihood perspective, because these are basically estimates of the Bernoulli random variable that picks image I or image J. So for learning from these pairwise comparisons, if you look at the whole corpus of your data, you only have these local empirical probabilities of Pij, and um, these edges only are present between some of your images, and the majority of your data typically doesn't have connection to any random image in your data set. So because of the limitation of pairwise comparisons cannot be scaled to basically have a fully connected graph, we have to come up with an approach that improves the quality of the learning approach. So, how do we learn from these pairwise comparisons? I mentioned earlier that what people typically do is they adopt an approach very similar to RankNet. RankNet was proposed in 2015, is perhaps the most commonly used approach for learning to rank from pairwise comparisons. What they proposed was you can train a network that um, at each step of training, it sees image A, image J, and image I, and makes a prediction for each score. And then you can use the cross entropy loss to measure your error, the training error, and then you sum that over your mini batch, and that you can back propagate through it and train your model. So this illustrates the way the models are typically trained for pairwise. You have an image I that is passed through your CNN model, and there's prediction as an outcome. Um, the weights of the network are kept fixed through weight sharing, and you pass image J, you make a prediction, and then you measure the loss, typically cross entropy between these two training examples. However, as I mentioned, the information coming through is only local, meaning that um, you only see the relative distance between I and J, not the relative distance of I and j between I and j given the rest of the data. What we propose is exactly that, which is one could aggregate and estimate the overall ranking of the images first. Let's call the the new empirical probabilities the global PIJs. We call them global because we assume that the global ranking information has been uh, distilled in these empirical probabilities, unlike the local ones. What we propose as just changing the training loss is instead of just using the local cross entropy, one can use a convex combination of the local cross entropy and the global cross entropy. And the parameter in the um, in the convex combination, we call it alpha here, and we'll show that it actually plays an important role in the training performance. So, in a nutshell, what we propose is rank the data first, then learn the model. Okay. So more specifically, I did mention that if you use a convex combination of the local cross entropy and global cross entropy, the net effect of doing that is actually as if you're averaging um, your local empirical probabilities with global empirical probabilities given the parameter alpha. And with alpha, you can swing this towards the local um, ratings, or you can swing it towards the probabilities obtained from rank aggregation. So I mentioned we're gonna approximate the PIJs, the global empirical probabilities by rank aggregation. But what is rank aggregation? So rank aggregation or rank centrality, how it works is that it constructs a Markov chain transition matrix given the local probabilities that we already measured. So let's call that matrix pi. And it has been shown that the stationary distribution of pi approximates the global ranking probabilities. And technically, all you need is the stationary distribution, and you can approximate the global PIJs. So, and a simple form of this is, for instance, a chess tournament, which players are randomly matched with each other, and they play, say, up to 10 games, for instance, and then players' scores are averaged, and then players are ranked according to that. That is a simple form of rank aggregation that one can imagine. So note that for approximating the the global empirical ratings, you only need to have the local ones. And for those local comparisons that you don't have them, basically, if there is no comparison done between I and j, the transition matrix essentially has zero. Okay. Another technique that we use in addition to the rank aggregation is we smoothen the estimated probabilities of the items results to improve the performance. This is a very common approach in when using word embeddings. You can use a parameter like beta to smoothen the probabilities of beta 0 equivalents to a uniform distribution, beta 1 identity, and beta larger than 1 basically skews the distribution towards more frequent and popular items. Okay, so with that, here are some of our results for learning from pairwise comparisons. We collected a set of curated data and we rated them to gather nearly 17 million pairs. The images we started with were a quarter million photos. For each pairs, we asked 5 human raters to compare image I and J, and a minimum of 13 pairs per image were used. We trained multiple backbones. What I'm showing here is results from Inception V2 model. And what you're looking at here is the accuracy of predicting um, the pairwise comparisons for different values of alpha. So alpha controls the smoothness of the probabilities. Alpha equal 1. If we go back, alpha equal 1 basically means that we put a lot of weight on the local cross entropy, and alpha uh, 0 means that we put more weight on the global cross entropy. Okay, so as you see, the best alpha was actually close to zero point 0.5, meaning that a combination of both local and aggregated probabilities helped to improve the performance. So on each tail, you'll see that training with only one type of ratings, local versus aggregated, results in suboptimal performance. Here are some visualizations and showing performance of the trained model for a few example images. And images on the top row are rather degraded by one type of blur, and the images on the bottom show higher quality overall. And you'll see both the predicted and ground truth scores. And as you see, the model actually is able to predict the quality very closely.